but otherwise please pay attention to what we're saying. So this coffee corner is a relatively new format. It's a bit shorter compared to our older webinar format called Special Interest Group. We're still focusing on making sure that you can use the PLAXIS software to the best of what we can advise you. And you will also be awarded a learning unit or a personal development hours certificate, and it will be added to your Bentley transcript. We'll come back to that in the next slide. I said that this will be automatically recorded and you will find the session on demand, usually within a few hours. If you want to see any upcoming events, please go to the Bentley events webpage and they will see upcoming coffee corners, answer hours, and other webinars to make the best use of your PLAXIS software. So as said, we also be watching for any comments that you have. So if you have questions, please add them to the Q&A. If you have other types of comments, please feel free to use the survey. We will keep watching that to see what type of other content we can deliver or what you're missing, or if you're not happy with us, please also tell us, because then we can improve. The certificate, it will be added to your Bentley transcript. So that's available at learn.bentley.com/transcript. It is connected with your Bentley profile. So you need to have a Bentley profile. It has to be using the same email address that you signed up for today. And then in this overview, you will be able to see all the events that you have attended. And from that page, you can also download this certificate of accomplishment. So those were the quick overview of the housekeeping rules. Today, I'm really happy that Vasilios here is presenting one of his passions is using geosynthetics as a very interesting construction material. So please, Vasilios, go ahead.
Thank you, Misha. Good morning, everyone. Good afternoon or good evening, depending on where you are in the world. And welcome to this Coffee Corner presentation. My name is Vasilios Bassas, and for the past 2 years, I've been working as a geotechnical support engineer with PLAXIS. So maybe some of you may already recognize my name if you have submitted a service request during this period. As you have already guessed by now, this Coffee Corner will cover the topics of using geosynthetics in PLAXIS. The presentation starts with a brief introduction to the geosynthetic materials and their applications in civil engineering projects. Afterwards, we're going to talk about a few tips and tricks where I will try to cover some practical questions, such as how do we determine the mechanical properties for my material, or which strength reduction factor value do we choose for the interface? And finally, why should we use an updated mesh with our geosynthetic analysis? Lastly, I'm going to demonstrate the design of a mechanically stabilized earth wall, or as we know it, MSE wall, which is after this presentation. Now, moving on to the introduction part, we're going to define geosynthetics in the general frame of the reinforced earth. So if we were to give, let's say, a more generally accepted definition for reinforced earth, we would say that it is a composite material formed by combining earth and reinforcement. I know that this sounds very simple and similar to the definition that we give for reinforced concrete. However, in this case, instead of concrete, our primary material is earth, and instead of steel rebars, we have another type of reinforcement, which is the geosynthetics. Geosynthetics, just like steel reinforcement in concrete, are used to withstand tensile stresses, which we know that soils are not very good at doing. Now, one might assume that the geosynthetics and the use of them are fairly new to the world, but that's very far from the truth. In fact, there are many findings that suggest that inclusions of different materials mixed together with soils have been used for thousands of years by ancient civilizations. For example, Romans used natural fibers, fabrics, or vegetation mixed together with soil to improve their road quality, especially when roads were built on unstable soils. The same, it was the same for the Egyptians back in the days of the pharaohs, where they used woven fabrics to stabilize roadways, and they also incorporated straw mats in the foundations of their pyramids. Finally, the Babylonians, more than 3,000 years ago, used reinforced earth to build ziggurats. The story goes that one of the, let's say, most famous ziggurats, the Tower of Babel, collapsed perhaps because it was not properly reinforced. So a fundamental problem that these ancient civilizations faced was using natural materials such as wood and cotton. And in a buried environment, they were facing an issue called biodegradation. Essentially, what this means is that the microorganisms in the soil were slowly eating away these natural materials. Luckily, this problem was solved in the middle of the 20th century with the coming of the polymer materials, which we know that when they are properly formulated and manufactured, they could last for centuries, even in harsh environmental conditions. Since then, the usage of geosynthetics has increased rapidly in many fields of civil engineering, including geotechnics, of course. And as you can see here, the global market is expected to reach $22 billion by 2027. Now, as we can see and observe here on the top, in terms of product, geotextiles dominate the global geosynthetic industry with over 70% of volume. Now, as you already know, geosynthetics have many areas of application in civil engineering. They always perform one or more of the following basic functions, as you can see here on the right. And they perform them when used in contact with soil, with rock, or any other civil engineering material. These functions are separation, filtration, reinforcement, barrier or containment, and drainage. As you can see here on the table on the left, for any given application of a geosynthetic, there can be one or more functions that the geosynthetic is expected to serve during its performance life. Now, in PLAXIS, the primary function that we typically model is that of reinforcement. So I put this in a darker green color here. In reinforcement, the geosynthetic develops tensile forces, and this development is intended to maintain or improve the stability of the structure. However, it is also possible to model barrier or drainage functions, but that could be a bit outside the scope of this presentation. And with that being said, I would like to take the opportunity at this moment to ask you this following question. If you are designing with geosynthetics, then which functions are most commonly used for your design? So the available options are separation, filtration, reinforcement, containment, drainage, or maybe some other. Of course, you can choose multiple answers if you want. And we can check the results in the next slide. So I will give you a few more seconds. So we'll have some time to answer this. Of course, reinforcement is the easiest function to model in PLAXIS, but as we said, we have other functions as well. So we can go ahead and check our poll results. So the majority of the answers selected reinforcement, but we also have some high percentages for separation and, of course, drainage. We're going to see some of the applications afterwards. So these are some nice results. So let's see some common applications in civil engineering projects. As we mentioned, the application areas of the geosynthetics they are numerous. One such application are retaining walls or what we know as mechanically stabilized earth walls. Now, geosynthetic reinforced retaining walls consist of different geosynthetic layers as reinforcing elements, and they are installed in the backfill to actually help resist the lateral earth pressures. Therefore, the geosynthetic reinforced retaining wall has three basic components. First, it is the backfill material, which is usually a more granular soil, we would say. Then second is the reinforcement layers, which are generally geotextiles or geogrid layers, but you can also encounter metallic strips. And last but not least, we have the facing elements, which are not actually necessary, but they are used either to maintain the appearance of the wall or to avoid any kind of erosion happening between the reinforcement layers. So we will be demonstrating one such example later on after this presentation. And with that, we can move on to the areas of embankments and slopes. As you may already know, the construction of embankments over weak or maybe soft soils can really become a challenge for geotechnical engineers. Now, in the conventional method of construction, what we usually do is that we first replace the soft soil by a more, let's say, suitable material. Either this or we improve it in one way or another. This improvement can be, for example, done with preloading, with dynamic consolidation, with soil mixing or grouting, or maybe with pile foundations. Of course, these options can be time-consuming, they can be costly, or they can be both. The alternative option here is to place a geosynthetic layer, which can be either geotextile, geogrid, or geocomposite over the soft ground, and then construct the embankment directly over it, as you can see here on the top right. In some cases where the foundation soil has voids or weak zones, it may be required to use one or maybe additional layers. On the other hand, in slopes, we know that many of the stability issues that we face in most of our designs are usually related to the requirements to meet steep grades without, of course, having to construct a retaining wall. In the end, what we want is to reduce the land requirements and provide additional usable area near the crest and the toe of the slope. Luckily, in recent years, the geosynthetic reinforced slopes have provided some very good solutions, which are both cost-effective and in some ways innovative for these slope stabilization problems. So they help us increase the factor of safety and stabilize steepened portions of the slope. Now, moving on to the shallow foundations, we know that the geosynthetic reinforced foundation soils are being used to support foundations for many structures. These structures can be footings, they can be bridge abutments, platforms, heavy equipments, etc. In usual construction practice, one or more layers of geosynthetics are placed inside the controlled granular fill, which goes underneath the footing. Now, the benefits of reinforced foundation soils are, first of all, the improved load-bearing capacity, and secondly, the reduced settlements. This happens because the imposed loads are distributed over a wider area. And normally, if we didn't have this, or if we didn't have geosynthetics in conventional, let's say, construction technique, we would need to have a thicker granular material, which, as you can imagine, it can be costly or maybe sometimes not even possible in sites where the availability of granular materials is not easy. Last but not least, we have the drainage, the drainage function. And we know that this function is associated with the increase in the rate of consolidation to have a more stable embankment or stage construction. As you can see also here on the left, on the images, the geosynthetics allow for free drainage of the foundation soils, to reduce the pore pressure buildup. The pore pressure buildup is usually underneath the embankment. So what happens is that the consolidation of soft foundation soil can be accelerated using these prefabricated vertical drains, or PVDs as we know them. And in PLAXIS, we usually do that using the drain elements, but again, that's a bit outside the scope, so I'm not going to go into more details. And with that, we can move to the, let's say, the more practical part of this presentation, which is the determination of parameters. We know that by definition, the geosynthetics have a slender structure, which means that they can only sustain tension, tensile forces, but not bending or compression. Therefore, it is important to know the tensile properties of our material. Tensile strength is usually determined by some sort of tensile testing, tensile tests. The most common one is the wide width strip tensile test, which we are actually gripping a geosynthetic specimen in the jaws of a tensile testing machine. And then we start stretching it in one direction at a prescribed constant rate of extension until that specimen breaks, or as we call it, it ruptures. Of course, we have many other tests that we can use. We have the grab test, the biaxial test, the multi-axial test, the plane strain test, etc. Now, during this extension process, we measure both load and deformation, and therefore we can derive at the end of the test some important parameters, such as the peak strength, the elongation, and the tensile modulus. So starting with the tensile modulus, we know, of course, that it needs to be considered in our design. Why? Because the geosynthetics need to actually resist tensile stresses under deformation. By definition, the tensile modulus is the ratio of the change in the tensile force to the corresponding change in strain. This is equivalent to the Young's modulus as we know it in other structural materials, such as concrete or steel. And you can see here on the top right, the figure shows a typical load strain curve for geotextiles. The tensile strength corresponding to the breaking points and the highest peak point, as you can see here on the top, are called the breaking tensile strength and the ultimate tensile strength, respectively. The slope of the load strain is the tangent modulus. And what we saw here as offset modulus, which is on the linear part, is actually the maximum value of the tangent modulus, and it is obtained by calculating the tangent on the linear part of this slope. However, we can have geotextiles that they don't have any linear range, such as the one shown on the bottom right, in which case the modulus is typically defined as the secant modulus at a specified strain. This is usually 5 or 10% strain. And now we need to translate all this into what we use as input in PLAXIS. So when we create a geogrid material in PLAXIS, of course, we need to define a few parameters. The first thing is the material behavior. We know that a geogrid can be elastic, elastoplastic, or viscoelastic. The second parameter is the axial stiffness, Ea, which can be acquired either by testing, as we saw earlier, or from the product specifications. Usually, the manufacturers provide the material specifications for the product, and the properties are usually expressed as tensile strength, Tmax, and the elongation at failure. In that case, the axial stiffness will be equal to the tensile strength over elongation. Last but not least, the third parameter is the allowable axial tension force in case of an elastoplastic material. When we are designing with geosynthetics and we want to consider its long-term strength, this property must be taken into account. So what we traditionally do in our design is to use a factor of safety approach. For example, for reinforcement applications, design codes use equations similar to the first equation that we saw here, where we estimate the allowable long-term tensile strength by dividing the ultimate tensile strength by several reduction factors representing the soil, the strength loss due to insulation damage, creep, and degradation, usually due to chemical or biological processes. For analysis procedures which incorporate the design factor of safety directly into the reinforcement, we use equation 2. Now, let's talk about the interaction that happens between the soil and the geosynthetic. This interaction, we know that, first of all, it's really important, and we consider it a key element in the performance of the geosynthetic reinforced soil structure. And it is important because the interface is mainly responsible for the transfer of stresses from the soil to the geosynthetic. In particular, for geogrids, we have 3 different interaction mechanisms that could be mobilized at the interface. The first one is the friction that happens between the soil and the solid surface. The second is the passive resistance mobilized against the bearing member. And thirdly, as also shown here on the right side, it is the friction happening between the soil, which is enclosed, means the soil in the gaps, in the openings of the reinforcement, and the surrounding soil. Now, the complex behavior at the interface is generally approximated by introducing an equivalent frictional stress that allows evaluating of the overall resistance. In order to study this interaction, we have created, not we, but many tests and theoretical analysis have been created and developed during the last decades. The most common tests that we have in our disposal are the direct shear test, the pull-out test, and the inclined plane test. On the right side, you can see some possible failure mechanisms. So at the top right, the sliding of the soil mass on a reinforcement surface is considered, in which case the direct shear test should be performed to quantify this soil reinforcement interaction. In the mechanism shown below, the reinforcement is pull-out, so naturally we're going to use a pull-out test. And finally, the inclined plane test is more suitable to investigate the interface properties under low vertical stresses, which is usually the case for barriers or for cover systems in landfills. Now, let's apply this to our PLAXIS input. As you may already know, when we define actually Geogrid, then we can also create an interface that goes with it. Usually we model the roughness of the interaction by choosing a suitable value for the strength reduction factor, which most of you know as R inter. And we do that by specifying a value at the interface subset of the material set that we have assigned to the surrounding soils. Now, in PLAXIS, the shear strength parameters of the interface can be obtained using a Mohr-Coulomb strength failure criterion. However, in this case, instead of a friction angle phi and a cohesion C, the strength parameters are expressed in terms of apparent friction angle, which is delta, and adhesion, Ca. These are parameters which are determined with the test that we have mentioned earlier. Therefore, the strength reduction factor becomes almost equal to the ratio of the tangent delta over tangent phi, which some of you may already know from geosynthetic design is termed as the efficiency of the geosynthetic. Now, having said that, we now understand that determining the correct parameters for our geosynthetics and their corresponding interfaces is really important. As we said, it's a key element. I would like to take a few moments of your time to ask you the following question, which is, in your designs, how do you usually determine these parameters? Is it usually through field testing? Is it lab testing that you're using? Or is it from the manufacturer's product specifications? Or maybe something else? So we will be showing the results later on, close to the end of the presentation. And I'll give you a few more seconds. I know that the first two options are sometimes costly, so people tend to use the product specifications. So I'll leave you a few more seconds, and then we can move on to the final part of the presentation. Okay. And the final part talks about the membrane effect. And to talk about it, we need to give an example of a geosynthetic which is loaded laterally by a vehicle. Now, on the application of the wheel load, the geotextile exhibits a more wavy shape. As a consequence, it starts becoming stretched. Now, in this stretched position of the geosynthetic, the pressure against the concave face is higher than the pressure against its convex face. And we know this mechanism as it is known as the membrane effect of the geosynthetic. So in short, we can say that the geosynthetics that are initially straight, they may become curved due to the lateral loading. And the higher the strains level gets in our analysis, the more apparent this effect becomes. Therefore, to take this curvature into account and to, in the end, to ultimately calculate the axial forces correctly due to the membrane effect, we need to activate the updated mesh option in the numerical control parameters. In simpler words, what the updated mesh does is that it moves the nodes in the mesh to the new deformed location, and it does that in every calculation step. And then it continues from there. This is, of course, different from the normal analysis, where the deformation is always calculated relative to the initial, to the underformed mesh. Now, although an updated mesh is usually recommended for geosynthetic analysis, especially when the lateral loading is present, due to the extra step that it takes to update the nodal coordinates, it can become a bit slower, and sometimes it can prove to be also numerically less stable. Finally, in a safety analysis, due to the consideration of the updated mesh, and therefore the more accurate, let's say, mobilization of the strength for the geosynthetics, the analysis could possibly yield slightly higher factors of safety. And last but not least, I think that this presentation would be incomplete without mentioning some of my favorite books on the subject. A big portion of the information, images, and graphs that I've used in the first part of the presentation were taken from these books, which I highly recommend to anyone who wants to start fresh in design with geosynthetics. And with that, we can now see the poll results. As we can see, the majority of our attendants have selected the manufacturer's product data specifications, which is expected. It's, I think it's both easier and also cheaper than performing some lab tests. And with that, we can now move to the second part of the presentation, which is the live demonstration of the design of a mechanically stabilized earth wall. So let's start with that. All right, so we are starting our journey in the soil mode. So let's hide everything and keep only our soil layers. Now here we have some mixed soil conditions with silty, sandy clay on the top 4 to 5 meters, followed by a clay sand and the silty sand. We also know that the phreatic level is approximately 3.5 meters below the ground surface. Now, as this is a very soft ground, we suspect that it won't be able to sustain the loads of the retaining wall that we want to build on top. Therefore, we have decided that we want to improve its mechanical properties in one way or another, which we will show later. Now let's move to the structures mode. Here we can define the geometry for our problem. So let's show everything and then hide the lines and the points. And we are left with these two polygons. The first polygon represents the outline of our mechanically stabilized earth wall. Here we have it in blue. And the second polygon represents the ballast of our rail embankment, which will be constructed on top. Now let's show the rest of the geometry. And to make it a bit more clear, I will hide the interfaces now. Yeah. So if you look at the foundation of the MSC wall, you will see that we have drawn a box. This box represents the area that will be improved. As we have mentioned in the presentation earlier, this can be done, for example, with soil replacement, with soil mixing, maybe grouting or piles. No matter which method we decide to use, we need to create a new material, which will represent the improved soil, and then assign it to this area. This area which we have drawn using simple helper lines. Now, another cluster that we have drawn using the same helper lines is this trapezoid here, where we have excavated the existing problematic material and we have replaced it with a more suitable, a more granular backfill material. Additionally, as you can see here, we have installed 2 layers of geogrids that will help us spread the imposed loads over a wider area. So after we've done these steps, we can start building upwards. And as we have mentioned, we have 3 basic components in our MSC wall. We have the backfill, and we have the reinforcement layers, which are generally geotextile or geogrid layers, but it's not uncommon to also have metallic strips. And for that, in PLAXIS, we use the geogrid elements to represent the reinforcement in this model. And finally, we have the facing elements, which we have defined as plates. As you can see, we have different colors for each set, which means that we are using reinforcement elements with different properties. This is, of course, natural and expected because we want to make our design economic and, of course, safe. Therefore, closer to the base where we anticipate to have higher horizontal soil pressures, we are also using reinforcement with higher axial stiffness and ultimate tensile capacities. Please forgive me for the colors that I've used in the model. I tried to select colors with high contrast, but as you can see, that didn't work all that well. Now, getting back to the geogrid materials, let's make the interface visible again. And each geogrid material has an interface, and this represents the soil reinforcement interaction. In this case, we have smoother elements, and after performing some pull-out tests, we have determined an R-inter of 0.8. That is, of course, a bit on the low side. So with that, after defining the geometry, we can go ahead and mesh our projects. I've already done this step. And then we can move to the construction, stage construction, where we start our initial stage with a K-Knot procedure, because we have horizontal layers of soil and horizontal phreatic levels. And our first phase represents the excavation and the soil improvement stage. Here we assign a different soil material with improved mechanical properties, as you can see here in gray. And depending on the improvement that we choose, it might be a good idea to also add an interface at the boundaries of this block to model the interaction which happens between the block and the surrounding soil. Now let's move to phase 2. It is the phase of foundation. We have the backfilling and the installation of the 2 layers of geogrids at the bottom. And we are also activating the footing, foundation footings, and the first layer of face panels. And after that, we start building upwards by adding consecutive layers of backfill soil, reinforcement, and facing elements until we reach the top, which is 10 meters above the ground surface. And then we get to put the cherry on top of the cake, which is none other than the ballast embankment. And last but not least, we have the combination of loads at the top of the embankment and the MSE walls, which actually represent the traffic load as per our design. After its combination, we are also running safety analysis, safety calculations to calculate the factors of safety. As you see here, I have completed the calculations beforehand. So we can go ahead and check the safety analysis first to see how our failure mechanisms look like. Now, this looks kind of scary, I know. It's good to mention here that the displacements shown in the safety analysis have no physical meaning. This is because when we are doing a safety analysis, the strength parameters are being reduced. Due to this artificial, let's say, strength reduction, we are introducing out-of-balance forces in our model. And this out-of-balance will be solved by the calculation kernel, which will in turn result into more deformations. So these additional displacements that have been generated have no meaning, but what has meaning are the incremental displacements or the incremental shear strains, which will give us a good indication of the likely failure mechanism, as you can see here. So we can check now the calculated factor of safety. We can do it in 2 ways. One is through the project menu in the calculation information, as you can see here. And another way is to go back in the stage construction and double-click the calculated phase. And if you scroll all the way down, you will find the reached values, which in this case is approximately 2.09. And we're quite happy with anything above 2. So we can go back to the output, and then you can show the results for loading combination 2. Now from here, we get an idea of the type of deformation for our MSE wall. Now let's increase the scale a bit. And as you can see here, there is a clear clockwise tilt of the wall and a distinct deformation near the right side of the foundation. Now let's change back the scale a bit again. So from here, we can check how well our geogrids have performed by dragging a selection window across the left side geogrids. As you can see here, I'm doing it from the bottom right to the top left, which means that I'm selecting any elements that have a part of it within that window. Now we can check the axial forces, and to make them easier to read, I have selected the wireframe option, and I'm scaling down the results a bit so they don't overlap. And from here, we can see which rows of reinforcements are loaded the most and how much of their axial resistance has been mobilized. Now, in both loading combinations, the reinforcements closer to the middle and the bottom of the wall have reached, or at least they are very close to their ultimate tensile strength, as you can see. Now let's close this and go back. Some additional information that we can check here are the principal effective stresses and their distribution close to the foundation. Let's scale the results down a bit. And we can see how the stresses from the weight of the MSE wall and the loading at the top are being distributed. And we can see also the direction of the principal stages and how that changes a bit over here. Another parameter that is very critical in our understanding of the potential failure, let's say, is the deviatoric strains, and more specific, the incremental deviatoric strains. And as you can see here, we have a clear surface developing near the right side of the foundation, which extends to a deeper depth. And we can observe something similar using the plastic points plot. Here we see that there has been some plasticity being developed within the MSE wall, but also closer to the foundation and within the improved soil, as you can see here. So we can go back to the deformed mesh. And this time we can check all geogrids together to get a better understanding of the general efficiency of our reinforcement. This time I'm dragging a window from top left to bottom right. And with this method, I need to have the whole element within my window to include it in my selection. So axial forces, and then I'll change the scale a bit. And you're going to notice here that the graphs from the left geosynthetics are plotted on top. And for the right geosynthetics, they are plotted at the bottom. This is related to how we draw the lines. So if we draw them from left to right, the plots will be on top. And if we draw them from right to left, the plots will be at the bottom. For loading combination 2, the right side has higher axial forces due to the eccentricity of the load at the top, whereas loading combination 1 is a bit more balanced in terms of axial forces. Now, we can go back to the first two inputs, and I forgot to mention a couple of things here. The first thing is that we can model specific connection between plate elements. We know that usually the facing plates of an MSE wall are free to rotate, so we can define the connection of two adjacent plates with hints. And to do that, we need to set the rotation to free. The other thing that I forgot to mention is that we can use a different elastoplastic material behavior. Now, geogrids can be modeled using what we have in PLAXIS as elastoplastic and epsilon behavior. So this material model allows the definition of the nonlinear stress-strain behavior for geogrids. When this plasticity, when actually we are defining this user-defined diagram, as you can see here on the table on the right, the axial behavior of the geogrid is actually governed by the defined force and strain. So typically the first segment of the N epsilon diagram determines the geogrid's initial axial stiffness. And the additional segments in the diagram define the geogrid's nonlinear elastoplastic behavior. And of course, the last defined N value, the axial value, is assumed to be the ultimate tensile strength at which the geogrid fails. Now, I've put some random numbers here, and if you watch closely, PLAXIS will not accept these values because what I've done is that I have put them in an increasing rate of change instead of a decreasing one. So I need to make a couple of changes in a few values. I will change this back to 0.5, and again, it will not accept it because I need to change this also. And this time it will be K. Okay, so this numerical modeling gives us the advantage of avoiding the, let's say, the difficulty of computing the geogrid axial stiffness, which we know that it depends on the strain level and the loading application time. Therefore, the axial stiffness is updated automatically at each iteration on the numerical model. And I think with that, we have concluded the demonstration. And we can move to the final slide, which is this summary. So So far, what we've seen is that reinforced soil structures have a long and successful history. Modern geosynthetic reinforced soil structures offer great flexibility. And we know that in PLAXIS, geogrids represent slender elements, which means that they have axial stiffness but no bending stiffness. So they can sustain only tension. And finally, it is really important to determine the mechanical properties and the characteristics of the interface correctly before we start our design. And we also seen the cases where an updated mesh is usually important in our case. And with that, I give it back to you, Misa.
Thank you, Vasilios. I think it's really a very nice and very comprehensive overview of the application of geosynthetics with a very nice case here for the MC wall. We added a few resources here. So in our Bentley communities, there are a few links that are very relevant to using this for geosynthetics. Before we're going to go to the questions, we have a question for you. There is a independent website. It's called g2.com. It's a peer-reviewed software website. So basically, it's like the Yelp or the IMDb, but then for software applications. And yeah, we also have PLAXIS 2D and PLAXIS 3D. You can see the links here in the page. G2 is an independent website, so it's not part of Bentley, it's not part of PLAXIS. It's really an independent website where actual users will do a review of the website to see and to share what is good or what is not so good about PLAXIS. So other people can make an informed decision. At the moment, we're running let's say G2 is running a charity program for any review. Now, review takes about 10 minutes to complete. And after that, there will be a $10 donation to the Water for People project. And the Water for People project is a cause that will that wants to bring clean drinking water to locations where there's no clean drinking water. And I think that's a very important cause to support. So we're very happy that G2 offers this charity donation program by reviewing a PLAXIS application. So yeah, if you can spend 10 minutes of your time, please do. Then yeah, then you will make our life better, but also the one for other people that are in the need for clean drinking water. So let's have some time for questions. Just as a side note, the certificate will be added to the learn.bentley.com/transcript, and it has to be tied to your currently connected email with this event, and then you will see it and certificate being added to your transcript within a few days. Okay, that's it for us. So now it's time to give you the questions. I think I got a very interesting question, Vasilios, here. The question is, can I consider in my design the actual forces taken from a safety calculation?
Yes, indeed, that's a good question. And the answer is, it depends. So as we have explained earlier, in safety analysis reduces the soil properties to a level where a proper failure mechanism or surface is formed. So the model is no longer stable. Now, during this process, the structural elements in our model, such as, for example, plates or geogrids, their structural forces start rising rapidly. So if you use structural elements with an elastic behavior, they will not fail, but they will continue to be loaded, which, as you may understand, this is, of course, not realistic. So during a safety analysis, in which structural elements are present in the model, there is a redistribution of stresses and forces, and these generally lead to the increase in structural forces. Of course, we have two options that can help us with that. The first one is to use geogrids with an elastoplastic behavior. In this case, we are introducing a maximum axial force, and this, of course, will limit the resistance of the structural elements. Now, based on the capacity of the structure, this may be the correct approach because it can improve the response of the system, which is the soil and the structure together, to more realistic values. The other option that we have is to, let's say, first run the safety analysis, specify the factor of safety in our model, and then once we have this value, then we can rerun the safety analysis using a target sigma MSF, which will be the target will be actually somewhere less than the value that has been already calculated. So what happens in this case is that during the analysis, the program will first perform the full safety analysis until failure, and then it will recalculate the last step before the target value of sigma MSF that we have defined. Of course, this will give the deformations prior to the failure, and therefore, let's say, more realistic axial forces. So, like I said, it depends, and certainly the interpretation of results that we take from a safety analysis will require a lot of attention and consideration, and certainly some of your engineering judgment. I see.
I have an interesting question here from your demonstration. Tamer asked here, what do the yellow dots at the face of the wall represent?
So these represent the connections between the facing plates. So the facing plates, like we said, are allowed to rotate. So we have defined a hinge between them, which means that we essentially have the rotation set to free. So the yellow dots are the connections.
Yeah, so basically this yellow dot represents a hinge in the model. Do I understand that correctly?
Yes, that's correct. That's correct. Another question here is, do I always need to add an interface to the geogrids? To the geogrid elements, I'm guessing. The answer is no. So whether you need the interface or not depends on the actual material and the expected interaction between the soil and the geosynthetic. So, for example, when we have geosynthetics such as geotextiles or geomembranes or even metallic strips, the main resistance mechanism are, of course, friction. So in those cases, you would expect to have a certain amount of slippage happening between the soil and the reinforcement. And therefore, it's a good idea, of course, to use an interface to be able to capture this kind of behavior. On the other hand, if you have geosynthetics that are, for example, like Geogrid or maybe Geocell, the resisting mechanism is different. Of course, in that case, we have the interlocking, which means that the interaction with the surrounding soils are more robust. In these cases, the efficiency, as we call it, of the material interface is much higher. So if we were to use an interface, we would set an R inter close to 1. So in that case, you might just want to leave the interfaces out.
Okay, clear. I've got a question here from Jose. On PLAXIS 3D, the parameter approximation, is it similar?
In PLAXIS 3D, the parameters are not in per meter of out-of-plane direction. So you are essentially defining a Young's modulus, epsilon, E, and the thickness, if I'm not mistaken, Misha, the thickness. So the thickness will give you actually the surface. So you define the parameters separately, because you have discrete polygons which represent your geogrid material, your geogrid geometry. So instead of having an axial stiffness, you have an elastic modulus and the thickness and the area, actually.
And of course, in PLAXIS 3D, you have to consider that you have to put in parameters for 2 directions.
Exactly.
So you have to specify your stiffness in the 2 local axis definition. But I think you can take the product of EA, which you have in PLAXIS 2D. You can also then put that as D times E in the PLAXIS 3D program. But then you have to separate input of D and the Young's modulus E.
Correct. Yep. Yes. Another question that I let's see. What is the facing plate material, EA and EI properties? So the facing plate in PLAXIS 2D it's a plate element. So the plate elements in PLAXIS 2D are considered to be rectangular. So what you actually need is the Young modulus and the thickness of your plate. So with the thickness, you can calculate the bending stiffness, which is the 1/12 times B, which is 1 meter times thickness in the power of third, and EA is Young modulus times the thickness times the 1 meter of the out of plane direction. So the only thing you need is the Young modulus. So if it's concrete, then probably it's somewhere around 30 gigapascal, and the thickness of the facing element. So after that, it's easy.
Yeah. A related question here. Somebody, Khaled, asked, what about the connection strength between the geogrid layer and the facing element?
Yeah, that's a
special measures that we can take there?
Yeah, that's a good question, actually. It depends on what level of detail you want to incorporate in your design. So these connection elements can be, for example, a different material that you define in your model. It could be, for example, a smaller plate or a different elastic material or elastoplastic, where you set it with a different strength. I'm not sure, Misa, if you have any more experience on how
Yeah, this is always tricky. Depends also really on the type of connection that you want to do and where you want to simulate the most critical part of the design in terms of deformations or in terms of strength. I can imagine that you might want to sort of design it such that the geogrid might break, or at least in your analysis you want to see when it will break at the connection point. You might then specify a small section for the geogrid material, and then you give it maybe a lower plastic axial force, so a lower tensile limit. So the NP value set to a lower value to make sure that if something breaks and has to yield or has to reach a limit in your geotextile element, then it would be at or very close to the connection point. You can also do it if maybe you want to have like a very softer behavior. You can give it a lower stiffness. So it really depends what you want to model there in terms of the how that connection should behave. And of course, if you think that the connection is much stronger than the whole geogrid itself, then you'll just use the geogrid properties.
Exactly.
So I hope that answers the question. All right, I'll see we're a bit past the top of the hour. So let's do 2 more questions, and all the other questions that we do not have time for here today. Yeah, please, we will try to answer the questions within a week. So we'll try to connect with you then.
See a question from John Uriarte. When there is no info about the R-inter, which must be used, what values do you recommend to use? For instance, when you have the geosynthetic above the natural soil, weak one as clays, and when you have backfilling covering the geosynthetic. Yeah, so there is no set values that we recommend as PLAXIS. These are values that we usually determine using one of the tests that we've shown, and they are directly related to the type of the geogrid or the geosynthetic and the surrounding soil. So it will be different if you have a geotextile and a geogrid, because the resisting mechanisms are different. So back to your question, the range of the R-inders that are usually used are between 0.8 and 1. But again, this depends on the combination of soil and geosynthetic. And of course,
I always look at the R-inter values as something about the roughness between the 2 materials that you're looking at, and when the interface between sort of your structure element, in this case the geogrid, and the soil is very rough, you get a high R-inter value. But if it's very smooth, or maybe there's a lot of water there, or maybe quick, easy local buildup of excess pore pressures, or you have like a very fat clay, then of course the geogrid will easily slip over this material, and then
exactly.
you have a lower R-inter value. So yeah, think of it like that.
Exactly, and
yeah, and it ranges usually between 0.5 and 1. Also, if I look from the R-inter factor between sheet pile walls and soil, you also look at that range.
Exactly, and like you said, because I have done some research in the past, the roughness of the geosynthetic is really important. So different materials, for example, you might have geomembranes that are from different materials such as PVC or HDPE, and because of their different roughness on the surface, they would have a much difference in the R-inter. So to answer the question of the user, the resistant mechanism is the most important one, but also the roughness at the point of contact between the geogrid or the geosynthetic in general and the soil.
Yeah, and maybe it's good to know that in your design you should try to avoid having this R-inter as the most critical or the most sensitive input parameter, because it's not easy to sort of get a very good and very exact measure for R-inter. So I would always advise to do a sensitivity study if you have the feeling that this R-inter value is of huge impact of your results. It should not make a huge impact if you go from 0.7 to 0.75. So with that in mind, yeah, have a look at the results and see if it's very sensitive to that.
Yeah.
All right. Let's see if we have one very nice final question here. I think I got a question here from Hesham. This is question number 5. Do we have an example, or do we know of an example where PLAXIS was used to model the case of geosynthetics as means of improving the bearing and/or settlement rather than stability problem? His personal experience showed little beneficial effect. Do we have such an example?
I think we have is it the pile foundation that we have also in our links?
Oh, yeah,
but
indeed.
But we don't have anything in the form of a model, but we have a couple of information in these. Let me check. Yeah, indeed, we need to somehow enrich our Bentley communities, and this is our goal actually on this topic of geosynthetics. So
Yeah, I will share the link here so that people can access that one. If it's not good, if you're unhappy or you have a case that you feel it should work but it doesn't work, make sure to reach out to our support team. You can fill in a service request. We also add also added this one here to the chat. So in the chat or in the Q&A box, you will find now a link to reach our support team. There you can submit a service request. And I would say, yeah, share your model there because then we can have a look to see what's going on, and then maybe have some advice to improve it or see where we can help to improve that.
absolutely.
Because I saw that you put some screenshot in the presentations about some elements about this reinforcement. If you think about the slide I'm putting in right now.
Yeah, the footing.
So this is the footing. So I guess it's referring to this case, where actually due to the
this is just
reinforcement.
Yeah, of course. This is of course a very simple case that I made to make a few checks.
Yeah. Okay. Did any new interesting question come up? No. So yeah, that's it for us for today. I would really like to thank you for your attention here.
Thank you.
And I have to thank Vasilios here, especially for giving this very nice example with this very clear demonstration of applying the geogrid elements for this MSE wall. So thank you for that.